right, in our last example, or examples here, we're looking at a study that was on pathology, and they ask us what the model predicts for the patient's high and low body temperatures, and then how much time is there between the spikes in the body temperatures. So what does it predict for the high and low body temperatures? That's going to deal with the amplitude and with the vertical shift. Okay, so I know that sine outputs -1 to 1, and so I'm going to go up 3 or down 3 from this vertical shift value right here. And so if I take that 101.6 and I add 3 or subtract 3, because that is the amplitude of the function, then I should get the highs and the lows. So for the highs, we're looking at 104.6, and for the lows, we're looking at 98.6. Okay, so it's predicting highs of 104.6 degrees and lows of 98.6 degrees, which is of course a normal body temperature, so that makes sense. All right, then how much time is there between spikes? So this is going to deal with the period. And so I know that I need to take 2 pi for the sine function and divide it by pi eighths. So 2 pi divided by pi eighths, that's the same thing as 2 pi times 8 over pi, and so I get 16. And so if I check out, let's see what the units on t are, they're in days, so about 16 days between those spikes of high to low. So 16 days is the period. So if I go from one spike to the next spike, it should take me 16 days. All right, so we were able to answer this question with our knowledge of period of a periodic function, and we're also able to answer with our vertical shift plus minus the amplitude in this piece down here. Okay, now the last part, topic 3, is about graphs of sums. So one of the more interesting and useful applications of periodic functions is the way that they add and subtract to form more interesting and complex periodic functions, and these can be used to model many phenomena. And so in example 6, sometimes when two tones are played on top of each other, they can overlap in interesting ways. We can model these effects with superimposed trigonometric functions. So first, we want to graph the function y1 equals sine of x. Okay, I'm going to zoom home so I can see this on the standard window right there. And I need to be able to see at least 2 full periods, and so we can definitely see that. We can see the first period is when I land back at 2 pi, and the second period is when we land back at 4 pi. So 2 periods goes between 0 and 0 and 4 pi. So 1, getting back to my starting place, 2, getting back to my starting place. Okay, and then next, graph another function, y2, and we'll call this one sine of 2x. Okay, before we graph, sine of 2x has a horizontal shrink factor of 2, so we should be noticing this graph happening twice as often because it's shrunk across the x-axis by a factor of 2. Okay, so in the next piece it says, what do you notice about where they touch, e.g. maxima, minima, or elsewhere? So I'm going to shrink this so that I can zoom in a little more. There we go. So you can see those still 2 periods. And they are not touching, I'm just going to click on a couple of their intersections. They're not touching at the extrema. They're touching somewhere off from them. They're not touching at the maximum minimum, but they are touching together or 0. So it's definitely elsewhere. They're not overlapping at the extrema though. So for that first bullet point, we can say that they intersect or touch close to, but not on the extrema. And we can also say that they have some of the same x-intercepts. Not all of them. There's an x-intercept here that is not reached, but every other one we do reach. So I'm writing this down again. So they touch close to, but not on the extrema, and at some x-intercepts. Not all. So we notice that. What do we notice about where the functions are both positive or both negative? All right, so let's look at the graph again. So where are they both positive or both negative? So I don't know if I can put it greater than 0. No, not on the same line. But I might be able to do y1 greater than 0 at least, showing me where the first graph's greater than 0, and y2 greater than 0, showing me the second graph's greater than 0. And so we're looking at intervals over which they're both positive right now. And so they're both positive about, okay, it's kind of hard to tell. So let me see if I can lighten these colors just a smidge. I don't want black shading. But if I do red and blue, the overlap is purple. Perfect. So the overlap is this purple section where they're both going to be positive. And so they're both going to be positive for, if I turn off that second shape for a second, it's for the first half of the positive of the original function. So they're both positive for the first half. So both greater than 0 for the first half of where y1 is greater than 0. And then negative, if we look at the less than 0 piece instead, the purple overlap, I hide one of my functions for a second, the purple overlap is happening for the second half of when the function y1 is negative, so the opposite. Okay. So they're both greater than 0 for the first half of where y1 is 0, and they're both less than 0 for where the second half of where y1 is less than 0. So they do overlap half of the time. Half of the time y1 is positive, they're overlapping. Okay, next, add these two functions together and create a new function, y3. So y3 next, add these two graphs. Add to these two graphs. I thought I said add them together. Sorry. Next, add to these two graphs a third graph, y3, which is going to be 2 times the sine of x. Now, this is just a vertical shift, so it's exactly the same as the regular sine of x. It just got taller. So do you see any common points among these 3? So this one is going to have the same x-intercepts as y1. So we'll make a note of that. y1 and y3 have the same x-intercepts. And then let's look at y2 in comparison with that. Now, y1 and 2 had those intersection points, but we're not going to intersect with y3 anywhere except for the x-intercepts as well. So y2 doesn't intersect y3 anywhere except the x-intercepts, and it's every x-intercept of y3, but every other of y2. So we'll just make a note that y2 and y3 only intersections, because those are the common points. They only intersect at y3's x-intercepts. Now try unselecting the previous functions and graph the following function. Okay, so we're going to turn those three off, but they're already defined. So when I graph a y4 function, that is going to be equal to y3, that's just the graph of y3, and we're going to add on y2. Okay, so now we have a sum of these two trigonometric functions. You can see some really interesting things happening here. So it does not look like the same cosine or sine function anymore. It's got some swishes going on there in the middle. So it is periodic. It does have a period, amplitude, and then some general shape notes. Okay, so this one has a period that is well, I don't know what this number happens to be. It's the same number on top and bottom, so it's going up to 2.598. I don't know why that particular value, but that is the amplitude. So it has an amplitude of approximately 2.598. What about its period? Didn't look for that last time, so let's look at that graph again. So remember that amplitude is measured from the horizontal, so you need to go up the same distance and down the same distance for it to be the amplitude. Then the period, this thing seems to repeat 2 pi. So I have a period of 2 pi. And then the general shape of this function, it's kind of like a sine wave, but it has that weird swish. So we'll just draw a little bit for its new shape. So instead of regular sine wave, we're going to swish as we come down, but not on the way up. So it's got that weird swish right there on the way down, which makes it different from the normal trigonometric functions, the ones that are the standards. Okay, the differences in shape that we see for different trigonometric functions added together or subtracted from each other is a way to mathematically model what we hear as things like tone, tenor, timbre of musical notes as they're played together. So experimenting with adding trigonometric functions can get us that kind of periodic function. So just for fun, what happens if I take a new function like y equals sine of x, and I add cosine of x to it? Didn't look too interesting, but if I subtract it, no, what if I multiply it? Okay, that's just changing some of the signs. And so what's more interesting is if I add cosine of 2x. Ooh, there we go. Now the period is changing. When I have the periods being different, that's when I see the most changes. So the 2 that we added here from y2 and y3, I got some interesting functions because they didn't have the same period. I'm adding functions at the same period. I didn't get quite as good change, but you can get really interesting things by adding varieties up there. If I add in some tangents, it's going to get real weird because tangent has those asymptotes associated with it as well.